next talk is on some science results from CassiniMIMI by Stamatios Krimigis.
Thank you. What I am going to be telling you is a higher energy version of a lot of the things that you've already heard this afternoon from the preceding speakers. The image that you see on the far left here, you may think that it is some image from ISS, but it's really not. What it is a picture from energetic neutral atoms due to the bombarding of magnetospheric ions of the atmosphere of Titan. And I will explain that in a minute. Let me just go on to show you the number of people who have worked principally on the instruments. There are more actually than this, about 30 people over the years, several theses, several graduate students who got their PhD. And the instruments that were used or prepared by the team, you can see the team here in 1997, when under the instrument, this is the so-called ion and neutral camera that was for the first time ever flown on a planetary mission. It was built by APR, by Don Mitchell and I and many, many colleagues here. The other set of instruments prepared by the MIMI team were the low energy magnetospheric mass spectrometer, LEMS. It was built at the Max Planck Institute, and Stefano Levi and Norbert Krupp were the principals. And the charge energy mass spectrometer, also hidden here under the blanket, called CAMS at the University of Maryland by Doug Hamilton and George Deckler. And the data processing unit that was built at CSR, and the lead was Yanis Dandouras. Now, these are what the instruments look like, but what you heard from Andy, for example, and the quotes about, you heard about this part of the energy spectrum. This is from 1 keV on. And the three sensors that you see here on the left covered first the traditional energetic particle instrument that is the equivalent of the instrument that searches for Van Allen belts in every planet. This has never been flown on a planetary magnetosphere planetary mission before, and it measures energy per charge. It tells us the identification and the charge state. And this is the so-called ion and neutral camera, and I'll explain that next. But before that, I'll show you this image, which Philippe showed you before. It actually comes from our paper in Space Science Reviews back in 2004. And what we have emphasized here, you see what we then knew from the Voyagers flyby of Saturn. And you can see the plasma sea, the Titan wake, the dust, and we have emphasized the fact that energetic particles interact with a neutral environment, both dust and gas, and then they escape the magnetosphere. And that's very important because I'll show you what it is that that meant. and the ring current, and so on and so forth. So what is this camera that we are talking about? I know some of you might have seen it, but look at this video. You have the magnetic field, and you have an energetic ion, which is obligated to follow the magnetic field, and you have some neutral out there. And what happens is at some point, they run into each other. So what happens is the energetic ion steals an electron and becomes neutral and escapes the magnetosphere. And now you have a detector where you measure the time of light and the total energy. And now you know that some ion that was in the magnetosphere that has escaped, you know its energy, you know where it came from, and the spectrum. So it's very simple. So you have H plus hitting a proton, and then it becomes an energetic neutral atom, and the neutral atom becomes charged. However, the energy transfer is essentially zero. All of the energy is carried by the original ion. Similarly, when it hits an oxygen, the same thing happens, and so on. So we were very proud of that instrument. Let me just show you, however, before I get into the other pieces of the instrument. This is the classical low energy magnetospheric measurement system. You see the pass through the magnetosphere. This is the magnetosphere and the Van Allen belt equivalent of Saturn. This is the instrument that was built by Max Planck. And you see the electrons and the energy range that they cover, the ions, the radiation belts, and so on and so forth. What you see now for the first time was also the mass per charge diagram that shows you that you have here, for example, H plus, H2 plus, helium double plus, helium plus, H3 plus, and a lot of oxygen. This is just from an hour's worth of data on the initial flyby. And finally, you see here a combination of what Larry Esposito showed you and earlier, and I believe Philippe. This is the aurora. This is the image now, the image that was obtained of the ions. And it highlights a connection. I will show you a movie later on. But let me just first talk about the composition. You've heard from several speakers about the soup of elements and molecules. Here is one example of one of the spectra. Mostly, you see a lot of hydrogen, a lot of oxygen, ions. Here, O plus, OH plus, H2O, water. What was one of the surprises for us is that, as you've heard from the previous talks, in the environment of, in the atmosphere of Titan, you expected on the basis of the Voyager data that we see a lot of nitrogen. And the idea was that, nitrogen would be shed and accelerated into the magnetosphere. But in fact, nitrogen was way down here. We saw some solar wind, 7 times charged oxygen. So we use the spectrometer to find out where did these ions come from and how they were accelerated. Now, one of the things that we all knew from the case of Earth is that there is a ring current that surrounds the globe, and it's about 3 years already in the magnetosphere. We found, of course, that the same thing goes through at Saturn. But instead of cutting through it here, here, and there, what you see is a picture of the ring current. And in fact, we find also that it's fairly dynamic, and I will show you a video if it works. So this is a video that we had in the same issue of Nature, and I guess I have to hit it again. No. I know it's there, and it did work before. No, go back. There is a video there. They are down there. Okay, it should work. No, it's there. No, if you just click the arrow. Well, I'm sorry, I did have my own laptop, but I was assured that it would work on this because it's also a Mac. Anyway, what I was going to show you is that you see this rotating about the planet, and you see it changing constantly. The ring current is not always there. And I'm already given the sign for the 5 minutes. I get credit for a minute. So here is what we made out of these images. That you have this is a schematic of the magnetosphere. You have a very thick plasma sheet up front and a thin northward tilted plasma sheet on the night side. And you also have ions that in the process of rotation, they escape into the upstream medium. I'm not going to get into that. I will, however, hopefully show you some of these. We detected a substorm. A substorm is a phenomenon that's well known in the Earth's magnetosphere. And here was a case where the ions began to increase, and here are the successive images. There is hardly anything there. Then you see on the midnight side a little increase, which keeps on moving, and you see it begins to envelop the entire magnetosphere. And at the same time, the Saturn kilometric radiation is beginning to pick up, and it really goes boom right here in all frequencies. This goes from about 10 to the 4th to 10 to the 6th KC, and you see the way these instruments work together with a magnetometer here. That's heard from Michelle, and how, so you can actually see a magnetic storm in action. The other thing that, okay, this video works, but I can hear the sound. Is there a sound? There is a sound here, but it doesn't seem to, it's, I should have used my laptop, I guess. Anyway, what you see here is the Saturn kilometric radiation from the plasma wave. You see that there is a big onset of activity on the pre-midnight side that it propagates, and at the same time you see the UV's aurora at all three things together. And it's the first time that we know where the plasma is coming from and where it's going. I have to move on. You already seen a version of this. Larry showed you the footprint of Enceladus with the UV aurora. This is the particles that we're seeing by Inca that connect the footprint of the field to the energetic ions that are dumped into the magnetosphere and generate the aurora, among other things. So I did want to show you the grand finale part. You've heard about that. What happened is that we detected that there is a radiation belt just inside the rings, which had previously imaged on the first flyby not flyby, but orbit. These are the rings that we knew about. And here's the new ring. Here is a blow up of that, and is modulated by a ringlet, a couple of ringlets, and the D ring. So this is just a summary, but it wasn't the only thing that surprised us. When we got into the inside the rings, we found that the instrument was beginning to do strange things. And it was responding, as it turned out, to dust that you can see schematically here that was coming out of the rings and coming into the magnetosphere, into the atmosphere of Saturn. And one of the things that happened is in the ion and neutral camera, where we had the high voltage, it dropped to zero, and it allowed these dust particles to trigger the instrument. And you can see here the difference, and you can see the count rate. So we had a dust detector that we didn't know existed. And I will finish with another thing that most people don't know about. You probably don't recognize what this is. When the spacecraft was outside the magnetosphere, we were able to look in the direction of the galaxy. And we discovered the heliosheath, the shell of energetic particles that surrounds the solar system. This is an image and that we turned into an artist's concept. But Voyager 1 crossed the terminations of the magnetopause and got out of the solar system at 122 astronomical units, Voyager 2 at 119. They were in this region when Cassini was making these images. It enabled us to get ground truth. And why is that important? Because for the last 60 years, the scientific community thought that the heliosphere looked like this, like a magnetosphere with a long tail of thousands of AU. Well, it ain't like that. The first observations that we have, and actually from what we know now from Voyager, this is kind of an image that we can forget. And the new picture is, I can hear the sound. That is the plasma wave instrument on Voyager, and the sounds from the galaxy. And I want to close with one picture, like everyone else, but kind of a sad one. These ladies and gentlemen are my best friends from graduate school days, who did a tremendous amount of work and discoveries for the planets and in the planetary medium, Dungarnet and Ed Stone, and of course, they're no longer with us. And this was a picture from an award to Voyager and Edstone for the Voyager missions in, I guess, 2014. So I was the youngest PI on Voyager. Now I'm the oldest PI on NASA, and I'm waiting my turn to go to the exit. Thank you.
Thank you very much. Any questions? Well, in one of your plots, you had a cosmic ray source. You can separate this source from the other energy sources?
Cosmic ray?
Yes.
Yeah, but in terms of energy density and pressure, that's a small amount compared to what we have in the rest of the instruments in the magnetosphere. But it did delineate the Van Allen belts of Saturn in great detail, and we wrote many papers on that. Any other questions? Well, let us thank Stamatios one more time.